In this lesson, you'll learn how to find and classify stationary points or turning points. There's 4 different types of stationary points. Okay, there's the maximum, the minimum, the inflection point, and another inflection point. Okay, in reality, these maximums and minimums, they might find us or show us on a graph where the maximum profit may be, okay, depending on the number of items that we sell. Okay, so we want to find that sweet spot to find the right number of items to make maximum profit. Okay, or conversely, we might have a different sort of graph where this is the number of employees. Okay, and here's the cost. And I want to minimize my cost of employees. So I want to find the number of people I should hire so that my total cost is minimized. These are just 2 examples of things where being able to find and classify stationary points will be helpful. The key understanding here is the one in bold. Okay, to find stationary points, find where the derivative is equal to 0. Because we can see in all of these turning points up the top, at the maximum, at the minimum, or at these points of inflection, we can see that the slope is 0. And remember, the derivative is the slope at any point. So let's have a go at doing one of these problems. I want to find the stationary points of this function, which is graphed to the right. We can observe graphically that there are 2 stationary points. We've got a maximum here and a minimum here, but we want to be able to find them algebraically because we may not be able to graph all of these functions. I need to find where the derivative is equal to 0. So first I'll differentiate. Okay, and I'll find that my derivative is 3x squared minus 6x. I know that at the stationary point, the slope is 0, so I'll write something to that effect. Stationary point occurs when f dash of x equals 0. Okay, so at this point, I'm going to now set f dash of x equals 0 and solve for x. So I'll put a 0 on the left-hand side. And then I'll solve this equation. I note that it's a quadratic equation, so I need to factorize and use null factor law. I've only got 2 terms, so this indicates to me that I'll just find a common factor between the 2 terms. I could take out 3x as a common factor, be left with x minus 2. Hopefully there's no errors there. Okay, and then null factor law tells me that either 3 equals 0, x equals 0, or x minus 2 equals 0. Obviously this first one is nonsense because 3 is never 0. Could have avoided this, by the way, if we divided both sides by 3. Okay, we would have not even seen this one because 0 and 3 is 0. Okay, but not necessary. We'd just get those 2 factors. Okay, so 3 equals 0, x equals 0 is one turning point, and x equals 2 is another turning point. If we look at our 2 points that we've identified on our graph, we can see that the x-coordinates of these points are 0 and 2. Okay, we also need to find what the y-coordinate or the function value is of these 2 points. So we need to substitute into the original function. Okay, so for my first point, I need to find what f of 0 is, which in my original function will be 0 cubed minus 3 times 0 squared. Okay, so it's telling me f of 0 is 0. So my first stationary point is 0, 0. Okay, on the other side, I've got x equals 2, so I need to find what f of 2 is. 2 cubed minus 3 times 2 squared. Okay, put it in my calculator, I'll find that f of 2 is negative 4. Okay, so 2, negative 4. These are my 2 turning points, 0, 0, and minus 2, 4 are the stationary points. So that's good. I know that there's a maximum. Actually, I don't know that there's a maximum. I know there's 2 stationary points. That's all I know at this point. I also need to be able to know whether these 2 points are maximums or minimums, maxima or minima, without just looking at the graph, because in some instances I literally won't be able to draw the graph. Okay, and I want to be able to automate these processes. So the way we'll do this is using a slope diagram, okay, in which we'll use the first derivative test or the table method, okay, whichever word you want to use, to classify them as maximums, minimums, or points of inflection. The way we go about this is by recognizing that for a maximum, at that point, the slope is 0. To the left of it, slightly less than it, the slope is positive. To the right of it, the slope is negative. Okay, so that'll help us in our slope diagram. Up, flat, down. Minimums look like this: down, flat, and up. And points of inflection can look like any of these 2 diagrams. We're going to use a table to assist with this slope diagram. This is what the table is going to look like. I want to investigate around these 2 points. Okay, the first one I'm going to look at is around x equals 0. So I know at x equals 0, the derivative is 0. I'm interested in what's happening a little bit below and a little bit above 0. So I'm just going to pick 2 points either side. To be convenient, I'll choose -1 and 1. And we can sort of see where these are on the graph. So here's a point at -1, here's a point at 1, and I can see that the slope here is positive, the slope here is negative, and it's flat on top. So it's going to be a maximum, but I should be able to do that without looking at the graph at all. So in here, I'm going to find the slope at -1. Remembering that my derivative is 3x squared minus 6x. So I'll substitute in -1. Okay, and this will give me a slope of +9. Okay, why am I writing the positive there? Because that's really all that I care about. I don't care about the number, just care that it's positive because it indicates that it's an uphill slope. At 0, we know that it's flat, and in here, I'm going to find what the slope at 1 is. So substituting 1 again into my derivative, okay, this derivative up here. Give me -3, which indicates a downhill slope. So from this diagram, I can tell that just from this little slope diagram, that the point that I've just imagined without looking at the graph is actually a maximum. So I can write that in my little summary here. So I can say 0, 0 is a maximum. I want to do the same thing for x equals 2, but I don't want to have to draw a whole nother table, so I'm going to sort of piggyback on the work that I've already done. I'm interested in what's happening at 2 here, so I'll put 2 in my table. I already know what's happening at 1, okay, I know it's downhill, so that'll form part of my diagram. At 2, the slope is 0. It's sometimes a good point to actually find what f dash of 2 is, just as a check. Okay, and you'll find that that is 0. Yep, 0. Okay, this is just a check. Okay, it's flat. So at this point, without looking at my graph, just looking at the table, I know I'm either going to have a minimum or this kind of a point of inflection. I just need to see what happens after this point. Does it go up or go down? So the way I'll do that is just by choosing some other random value, whatever you want. I'll choose this point at 3 and see what the slope is on that side. Okay, so I'll put 3 in here and I can find what the slope is. Okay, substitute these values in. Get a slope of 9. I don't really care about the number, just that it's positive. So from here I can conclude that 0, 0 is a maximum, and 2, negative 4 is a minimum. When you're doing these problems for real, all of this stuff around here, don't need to write them all out. Maybe just write out the first one to show that you're substituting into the derivative. Is there any other way that we could check this? Yep, we can draw a graph on Desmos, okay, or we could draw a graph on our graphics calculator. I'll type my original function into my calculator. Okay, I'll draw it. Can't really see it, so I might just zoom out. Sounds good. Okay, from here I want to find, what's the coordinates of this maximum and this minimum point. For that I want to G-solve, so F5, and I'm trying to find some maximum value. It'll think for a second and then tell me it's at 0, 0. Okay, confirming what I did algebraically. If I want to find some minimum value, I'll get the same thing, 2 minus 4. Okay, and this is some sort of a diagram, okay, that you could capture and paste onto your digital exam paper when you're watching this video in the year 2020 and we actually have digital exams. Okay, but until then, you'll just have to hand draw this calculator output as a justifying of your result. So that's the table method. There is another way to classify these turning points. So just to summarize, finding is just finding the actual points. Classifying is saying whether they're maximum or minimum. There is a second method to classify these using the second derivative test. Okay, so the finding part will be exactly the same. So I can just copy and paste that from the previous example. So the finding part is exactly the same, found the same 2 stationary points. Okay, the classifying part is different. In this case, we're going to classify them using the second derivative test. Okay, so in classify. Okay, second derivative means I need to differentiate again. I've got a derivative currently. I need to differentiate it again. So f dash dash of x means differentiate the derivative again. Just using the differentiation by rule, end up with 6x minus 6. So the idea is this second derivative is really the slope of the slope function. This is my original function. This is my slope function. Okay, the second derivative is what's the slope of, say, this random point here, the slope of the point on my slope function of the original function. That makes sense, doesn't it? Yeah, sure. Good. Okay, the slope of the slope function. So let's have a look at what we can do here. If I want to classify this turning point, the first turning point, 0, 0, all I need to do is find what f dash dash of 0 is. Okay, the double derivative of 0, or the second derivative of 0. Substituting 0 into my second derivative, 6 times 0 minus 6 gives me minus 6. Okay, so because that's a negative value, in this chart at the bottom, I circled the wrong one. If the second derivative is negative, your stationary point is a maximum. Okay, so I can say 0, 0 is a maximum. Okay, so I'll just note here that it's negative. Okay, therefore 0, 0 is a maximum. You might be thinking, what's this d squared y dx squared? So if I'm using y equals notation, my derivative can be y dash or dy dx. My second derivative would be y dash dash or d squared y dx squared. Okay, just like this one down here. It's just a different notation. Okay, so you're probably wondering, all right, that's great to have a rule if the second derivative is negative, slope's maximum, but I sort of want to know what's going on because I'm a good student and I care about knowing things. What this is saying, second derivative is negative, means that at this point, okay, I know that on the slope function, this is flat, so I get a 0 slope. Where we can extend on that is by looking at the instantaneous rate of change at this point. It's a negative rate of change, which means that negative rate of change and passing through 0, which means that the slope went from a positive slope to a negative slope, which we can see on this graph. Positive slope to negative slope. So that indicates to me, in terms of a slope diagram, positive, 0, negative, indicates a maximum. Okay, I'll have a look at what happens when I try to classify the other turning point. So I need to find what f dash dash of 2 is, or the second derivative of 2. Substitute 2 in here, I'll get 6 as my second derivative. Again, I don't really care about the value, just that it's positive. Okay, you need to note that it's positive. If the second derivative is positive, your stationary point is a minimum. Okay. 2, -4 is a minimum. Okay, again, I can just read this test summary, or I'll try and understand what's going on. At this point, 2 minus 4, I know the slope is 0, so there's my 0 slope on my slope curve. By looking at the second derivative test, I know that the slope of the slope function at that point is positive, which means it's going from a negative slope to a positive slope, which we can see on the diagram, negative, flat, positive, negative, flat, positive. So it means that it's a minimum. Okay, so I'll just write some words in here using the second derivative test. Okay, so you might find the second derivative test easier, up to you. The only problem is, if the second derivative is 0, you can't use the second derivative test. You need to turn back a page and look at the first derivative test to determine whether it's maximum or a minimum. Most of the cases you see where this is the case will end up being points of inflection, which you'll find out using a slope diagram, looking something like that. So in summary, you have just one way of finding where the maximum, minimum, or points of inflection are, which is by finding where the derivative is 0, and you have the second derivative test and the first derivative test, or the table method, to classify and find out whether they're maximums or minimums without having to graph it. Okay, from here, I want you to have a go at these questions at the bottom. Do the odd numbered questions using the first derivative test and the even number ones doing the second derivative test, so you get a bit of variety in both. Also remember that our notation, if I've got f of x, it goes down to f dash of x for the first derivative and f dash dash of x for the second. If I've got y equals, I've got two choices. This can be y dash or y double dash. This can be dy dx or d squared y dx squared. Okay, all of them the same way. There it is. Good luck.